Hi everyone, welcome to DBA712 Research Methods for Business, and this video is to help you with assignment 4. And what I'm going to be talking about today is how do we go about doing quantitative data analysis at a basic level. So we start off by looking at analysis of differences and analysis of association. And then I'll give obviously some pointers towards the assignment. Just to let you know that there are also what we call multivariate analysis, which are multiple dependent variables. We don't really cover them in this subject. It's very hard to cover everything in a subject, but certainly that's something you need to talk to your supervisor about if you're going down that path. Okay, so let's firstly talk about the difference between descriptive and inferential statistics. This is something that's probably kept you up for a number of nights. Descriptives are essentially what describe the characteristics of a population. So we've got things as basic as frequency counts. I'm just going to move this up out of the way here. Right down there. Frequency counts, means you would have heard of, median, which is the middle of a population, so you would have heard about median house prices. That's a measure of the median as well. And then we talk about dispersion, which is really the variance or the spread of the population around a central figure being the median or the mean. So in terms of inferential statistics, that's when we're trying to infer something, either that two things are different, that property prices in Sydney are different to those in Perth. And you might think, well, yes, they are. They're significantly higher. But what we're interested in here is this significantly high? Is this a result that could occur by chance, or is there something to it? Or what we call association. Now, association are things like levels of smoking being associated with heart disease, the amount of exercise you're doing being negatively associated with your weight. So these are often come, as you would have guessed, from medical research, but often they're used now in business research as well. Okay, so here are some measures of dispersion that are often used, and you can see one of the first ones, which a lot of people forget about, is the range. So what is the minimum score, maximum score? Now this is particularly useful if we're trying to find miscoded variables. So let's say we had an age measurement, and if you've got somebody who's 300, unless it's biblical, you've obviously made a coding error. That age was probably meant to be 30. So likewise, you wouldn't have somebody with an age of 0, so perhaps it was an age of 30 and they've missed the 3 on the start. So range scores. Deviation scores, how far they are away from the mean, or if the median, we might talk about quartile ranges and so on. And that's often called the average or standard deviation. And variance is just simply the square root of the standard deviation. Sorry, the square. Now, the kinds of approaches you use, I'll just move myself up here, depends upon the level of measurement. Now, you'll need to read what I've said a bit earlier about this. I've written quite a good textbook that you might want to look at this area that you can get from the library here, or consult any good market research text in this area. And basically, the kind of tests, measures we use depends on what we call here the levels of measurement. And so nominal, which are things like gender, the colour of this jumper, which is pretty terrible. We might use simply the mode, how many green jumpers are there in the building? And the answer is 1. Ordinal, which is a measure which has an order, but the intervals aren't equal. We can use what's called the median. So we could talk about the median educational level in this building, which is probably a PhD. Interval or ratio, these are probably what we might be familiar with. So rating scales from 1 to 5 are interval, because the intervals are equal. And we can talk about an average attitude, or we could talk about an average age, weight, income. These are all, if you like, usually these measures will have a 0 or an equal interval. Now, it's important because these types of measurements later on will determine what kind of analysis you can do, as well as the question you're asking. Okay. Just some other things that you may have been familiar with if you've done statistics before, but basically when we are measuring anything, we're taking a sample. So even if you're measuring my height today, that's a sample taken today, and although the height might be roughly the same tomorrow, if you look at my hair here, it may be by the end of semester a little bit less. So it's what we call a confidence interval around any sort of measuring, which is the population mean plus or minus the sampling error. So as you would imagine, the larger the sample you get, the less there is an error in measuring it. And the percentile is that the probability that the results are correct. So when we, for example, take a poll in the election, you would have heard about this thing about an error amount. And the error amount times how confident we want to be about the results, 95, 99% in a very close election, determines how close the estimate actually is. So if we're not that worried about my height being 5 or 6% difference, well, you need a smaller sample. If we really want to sample to 1% probability of trying to estimate the election result, and that's difficult because we're dealing with intentions, not behaviour, then we need a much larger sample to be that correct, because people's attitudes and behaviours vary. So, related to that is then what we call a hypothesis. So when we're talking about inferential statistics, we're talking about testing whether things are the same or different, which is a test of difference, or whether things are associated, whether there is an association between someone's income and voting, say Labor or Liberal is a classic example of that. Now, the way science works, of which statistics is part of, so mathematics and statistics, is to start with a statement of what we call the null hypothesis. And really, what we do, which is kind of weird, is to find evidence to reject the null hypothesis. And that's usually, in statistics, that the two populations have the same income. House prices in Perth and Sydney are the same. That's the null hypothesis. The hypothesis we're testing is that they are different and one may be higher or lower than the other. And so from that then is which we often call the alternative hypothesis, H1 and H0. So hypothesis are often what you write up in your lit review, if you're doing a quantitative study. Then when you go and do your analysis, you are finding evidence which rejects the null hypothesis, which is that there's no difference and it's due entirely to a random sampling error. So the growth in Bathurst house prices is the same as that in Sydney, and that's the null. And of course what we're really trying to say is it's different. And the alternative hypothesis, which you get from disproving the null, is really that there is a difference between house prices, say, between Perth and Sydney, or growth rates in Bathurst are indeed higher than that in Sydney. If you're obsessed with property, this is a good idea. Okay. So this is really just giving you a more example here from research. So we're in business research. This is a marketing example. Why? Because I teach marketing. So the null hypothesis here. So the example here is, as somebody may have written up in their literature review and in their design, highly dogmatic consumers will be less likely to try a new product than less dogmatic. So dogmatic are people who hold very strong beliefs. They're less likely to change. So the null hypothesis is no difference between high and low dogmatics in their willingness to try an innovation. And the alternative hypothesis, which you get by disproving the null, as I said, is that there actually is a difference. Okay? Now, to test the difference, I'm just going to move myself around a bit here. To test the difference, you then have to look at how certain you want to be that actually the two things are significantly different. And so the rule of thumb that we use in social sciences is usually, but not always, 5%. Okay? So if the probability level is 2, so basically what we're saying is, with a 5% level, the probability this occurred by chance is very low, 5%. In other words, we can reject the null. Okay? Or we can be 95% sure that the alternative hypothesis is correct. But remember, we're always testing that the null, or providing evidence, or trying to find evidence that the null is actually not so. Why will become clearer in a little while. And I guess it has to do with the scientific method. Things stay as they are, the status quo, unless you can prove otherwise. And so the statistics is based, analysis is based on that approach. Now, there's two types of errors that creep into whenever we do anything probability. You can't have an error-free world, unfortunately. Type 1 error is that you reject the null hypothesis when it's true. And so what we're saying is you find evidence for so we've rejected the null hypothesis when we've rejected the null. In other words, we said that there was a price difference between Ballarat and Bathurst when actually there isn't. And that's what we call a type 1 error. Most research is really about a type 1 error. We don't want to make a mistake of incorrectly rejecting the null hypothesis. Why? Well, if I was a property developer and I was looking at investing either in Bathurst or Bendigo, and I find there is actually no difference, but I think there is a difference, then that would have cost me money. So it would have been better not to spend any money. So that's one way of thinking about it. Type 2 error is failure to reject the null hypothesis when the alternative is true. So here, there actually was evidence that that there is a difference in prices between Ballarat and Bathurst, but we haven't rejected that. Type 2 errors are particularly important where the consequences of that kind of failure are particularly high. For example, rehabilitation in prisons. You don't want to send somebody out of prison who is not capable of being rehabilitated. Therefore, probation boards are often quite cautious about releasing people earlier. Now, another way of thinking about this, and sometimes analogies are useful here because type 1, type 2 error, it all probably sounds gobbledygook to you. But if you are in a legal case, like this gentleman over here was, who was the Rainey case, Lloyd Rainey, and he was accused of murdering his ex-wife. Now, why there is significant suspicion, the way that the court of law works and the way statistics works is by disproving his innocence beyond a reasonable doubt. Hence the very high level that, the chance that this occurred by other factors is so small. Reasonable doubt, 5%, or we're 95% sure, then he's guilty. Now in this case, although people have a lot of suspicions about what went on here, the man is innocent because there is not sufficient evidence beyond a reasonable doubt. And beyond a reasonable doubt, in statistics means there's a very low probability this result occurred by chance. Hence, 5% is usually the rule. Okay, so here's an example using what we call a t-distribution. Again, I won't go too much into specifics. I'll just try and move myself a little bit out of the way. Here, I'll make myself a bit smaller. Let's see how this works. Okay, let's move myself over here a bit. Okay, so the way that this works is that store manager believes the average return on exchanges is 20. So I'm getting 20 exchanges. And so the manager, that's his benchmark, that's what he can afford, records returns for 25 days and has a sample of 22, standard deviation of 5. Okay? So the confidence interval is given there, and referring to a statistical table that you get from working out the t-distribution, you find that distribution fits in the tail, in other words, is less than 5%, and that therefore the null hypothesis can be rejected. So this is a very simple thing that the proposition starts, there actually is no difference, and we are testing that, and these results here show that in fact there probably is a difference. Therefore, his returns are significantly higher than what he expected. So he needs to change his policies. Alternatively, you can do this by the t-value, which is worked out here, which is the mean, less the standard deviation, less the sample, the benchmark figure, which is 22 minus that, times the sampling error, so that's the standard deviation, divided by the sample size. So you can see, the larger the sample size, the smaller this number down here gets. Okay, so we find that the t-value is less than the critical value, which is usually 2.034, then the null hypothesis can be rejected. Okay, so that's a simple example. Now, how do we then pick the right test? Well, as I've said, if you're looking for a test of difference, this is one where you're just comparing it to a benchmark figure. Are all academics aged over 50 or not? That might be one. And age is a t-test, or what we might call a z-test. If you're looking at whether a satisfaction level of 5 in a student survey is lower or above that of the sample mean of 4 for a school, again, I say School of Marketing Management Marketing, then you might do a t-test. Ordinal is the Mann-Whitney test or the z-test, and this is really saying, well, is there a difference between educational levels of men versus women, or is there a difference in income levels between Aboriginals and non-Aboriginals, for example. For nominal, so things like men, women, and whether they wear green jumpers or not, then we would rely on the z-test or the chi-squared test. So the two fundamental questions you've got to ask yourself are, firstly, is this a test of difference? What we're doing here. Secondly, what is the level of measurement? Okay. Okay, so the chi-square test, as said, or I've talked about earlier, allows for the investigation of frequency stuff, things like sex, education, and so on. And it's really a measure of observed frequencies with the expected frequencies, and the expected frequencies are the categories are equal. In other words, that men and women wear the same number of green jumpers as the expected, and of course the observed is what actually is occurring in the building. Test about whether the data come from a certain probability distribution, which is called the chi-square. So the process follows is finally formulate the null. So the null is really that there is no difference across the categories. You calculate the chi-squared value, then you look up the table from a chi-squared table. Luckily, we have this wonderful program called SPSS, and they help. That helps you look at. That does calculate this for you. But what you've got to be able to do is interpret the results. So here's another marketing example which just shows this chi-squared in operation. Okay, so what we have here is we have one way of people being either aware or not of the manufacturer's brand, and we've got a frequency count from a sample that we took in a questionnaire of 100 people. 60 were aware and 40 were aware. So we're just trying to say, right, is there a difference between these two? Is there a statistically significant difference? And so you can see how it works. We take the observed frequency, we multiply by the expected. Expected is that it's equal. We take the observed minus the expected, and then we divide by the expected, and what gives us that result there. Okay? Squared, sorry. Okay, and that's what that's showing here. So it's the observed minus the expected squared, difference. Sum that up across all the tables, and that gives us the chi-squared statistics. So it's 4. Degrees of freedom is the number of things in the cell. So we've probably got 2 there, right? Times 1, so it's 1. Okay, 2 categories, so 1 degree of freedom. And the chi-square is 3.84. If it's larger than the critical value, the null hypothesis then is rejected. I'm just moving myself around a bit. Okay, so some other tests. Well, the level of bivariate tests, here we're now starting to look at across 2 groups. So far we've just compared things like comparing a certain benchmark figure or whether 2 scores were different. Here we're now actually starting to look at bi means 2, and we're just saying, well, what are some of the measures here? And you can see they're roughly similar. The t-test for the interval and ratio down here is commonly used. If we had more than 2 groups, so if we're looking at differences in income levels from Perth, Melbourne, Sydney, then we would use what's called the ANOVA or analysis of variance. More on that later. ordinal differences of ranks between, say, men and women in terms of education, I talked about earlier, and the chi-squared test, often used when people are looking at cross-tabulations, whether there are differences across all the cells. So, just another example here. Okay, can be used to test a hypothesis stating that there are two mean scores and so on. The other is nominal scale with two groups. For example, here we've said frequency of purchase, how often people buy something between men and women. Do women buy more shoes than men? Not surprisingly, they do. Okay. Not all women, but on average, right? And so, the null hypothesis, there's no difference between the means, or the mean difference is 0. The t-value then is worked out to test the null hypothesis. So it's the mean of group 1, mean of number of shoes bought, less that of men. The variability of the means, which is a pooled standard error. And again, the lucky thing is you don't need to calculate this. Okay, this is just showing you an example here. Now, as you can see, here are some differences towards recycling, and we've got, it looks like art students recycle more than commerce students. There's some variability around the sampling, and we pull that variability, and once we do that calculation, we end up with a t-statistic of 2.34, which we find that the null is rejected. That is, that these two groups are different. So we have enough evidence to say the groups are different, and therefore that art students actually recycle more than business students. Here's another one, arts and commerce students, number of public protests attended, and it looks like it seems to be a little bit more for art students. So this is really what you get if you run the analysis in SPSS. So first it gives you the mean scores, the standard deviations. The standard error of the mean is just the standard deviation divided by square root of sample size. Variability, really. Then you get this strange level of analysis, which I'll talk about down here, which is what SPSS gives you. By the way, where do you get SPSS? If you look at my notes, there is a link in the guide to assignment 4, which says where you can download a free trial copy for 14 days. So have a look at those notes. Okay, so what I'll do is just go on to the next slide, then I'll flick back to what I'm talking about here. So the mean is displayed in 13.2, but is it real? Did it occur by chance? The equality variance is what is explained down here. The first test says whether there is any difference in variance between these two groups, within these two groups. And actually it finds that there isn't. If there isn't, we go to the second line, which is the equal variance is not assumed. Because it fails this test here, we look at the t-values here. Now generally these don't vary that much. Okay, and we can see that the value here is 2.31, and that gives us a probability of 0.032, which is less than 0.05. Now, the thing to remember about statistical tests, it's a bit like being pregnant. You either are pregnant, there is a statistical difference, or there is not. So if we had 0.06, then we basically say it's not significant. Some people sometimes say, well, it's significant at the 10% level. But once you set that benchmark, that's it. So there's no such thing as highly significant, nearly significant. You are either pregnant or you're not pregnant. There is either evidence for difference or there's evidence for association. You're either innocent or you're guilty. Okay? And this next slide just explains kind of what I'm talking about here. Okay, so the equality variance is on 13.3. We can assume equal variances. So the two means are significantly different, and that's what we're saying there. So what this figure here is saying is that the probability this occurred by chance is extremely low. It's about 2%. So then we're fairly confident that actually art students go to more public protests than commerce students. Okay. Now the analysis of variance is similar, but the test's quite different. The question it's asking is the same, but now we're starting to deal with two or more groups. Working full-time, part-time, outside the home, willingness to purchase life insurance. Now, the null hypothesis is about differences in means, but is also about differences in variance or variability around each of those means. And the way it simply works is it's saying that the variability for the null to be rejected is that the variability within each of these groups, right, is less than the variability across all these groups, right? So if you've got a lot of variation in each of these groups, but that means that it will be harder to find variation across all these groups, okay? Alright, so it's often called an overall analysis of variance. And the grouping variable here is working status, so it's often a nominal measure. Okay, it can be ordinal, but it's normally nominal. The F-test is used to compare the sample variance with each other, and again, this is another distribution with appropriate statistical probabilities associated with it. Okay. Larger variance between groups implies a greater F ratio. If the F ratio is large, usually bigger than 3 from memory, the more likely it is that the differences occur as a result of the grouping variable. In other words, that we've rejected the null. Thus, the null can be rejected. Here's an example. Okay, so this is what you might look. This is actually what you get from SPSS. Now, remember I talked about the sum of squares. This is the variance between groups and within groups, and this is the total sum of squares here. And you can see here that the variance of purchase likelihood, okay, so we've got various prices from $65 to $75, that actually there is so much variance within the groups. You can see it's a very large number within, so that's within 64, 69, 74, then between, which is 64, 74, all that together, that really the F value, which is that divided by that, which gives you that score there, is very low, and we haven't found enough evidence. So what we conclude here is there doesn't seem to be any difference from about $65 to $75 in purchase likelihood according to price. Okay, so what a manager could do then is obviously set the price at $75 and would be reasonably confident not losing a lot of sales as a result of that. Remember, we're dealing with a sample though all the time. Some groups are more sample than price sensitive than the other. Again, this is really talking about 0.5, it's not significant, so it's a result of sampling error or chance that I've just talked about there. Now, the Mann and Whitney test is a test of ranks. Here I've just simply done a test of ranks in terms of exam results from a subject I taught a while ago, and you can see here that indeed the men in this subject did significantly better than the women, and the two-tail measure there is given as this result. And again, this is the sort of output you get from SPSS. You don't need to calculate this, but you do need to interpret what the computer tells you. So there's also a couple of things you should be aware of. There's a lot of people think, well, things are statistically significant, therefore they're practically significant. And actually, the two are sometimes related, but other times they're not related. If there is a statistical difference, the practical difference might be very small. So why would that occur? Well, we've got a very small variation in the sample size. The variance might be, the difference might be small because in terms of 5%, but it may not make a lot of difference to a company's bottom line. So there might be a difference between my attitude towards breakfast cereal and my attitude towards poached eggs, and it's statistically significant, but does that really make a difference to the overall sales of eggs and the overall sales of breakfast cereals? And even across a sample of 200, 300 people, the answer may be not really. So the practical difference might be very small. Now, that doesn't mean if it's important. If we're dealing with things across a large population, for example, differences in financial property prices, a small difference might be in a large multi-billion-dollar portfolio, it's significant. or if we're dealing with rates of cancer, which are normally quite low, a small difference might also be important. Okay? Sorry about that. It never stops around here. Okay, whoops. I just want to go back and make another point. Researchers need to keep this in mind when they're interpreting output. What is the scale of the difference between the two groups? Okay? So, okay, I found a difference, say for example, between the number of protests arts students went to and business students went to. But the difference is really quite small. The number of protests is really quite small. So, really this is not an important issue here. Okay? So, a couple of things to remember then. Some rules of thumb. It's always good to have rules of thumb. The type of question depends upon, the type of analysis depends upon your research question. Right? So, concerned with comparing average monthly sales across two groups, or a central value might use a t-test. Number of variables. One variable at a time would use a univariate, it's like a benchmark figure, or a bivariate approach. Scale of measuring. So mean requires interval or ratio scale measures. So you can't do a t-test on whether men or women have green jumpers. You have to do a chi-square test for that. Parametric, which is really what we mean, that something has a mean, or non-parametric. So things like green colours, colour of my eyes, gender, school you went to, state you live in, etc. Categorical variables is another name for this. And we call those kinds of measures non-parametric. And those also include rank measures like income categories and education. Hopefully this has been useful for you and it helps build towards your understanding of assignment 4. Thank you.